So our next unit is more straight geometry, less algebra stuff. For some of you that's good news, for some of you that's bad news. It's just the way that it is. We'll be doing a lot of stuff with triangles. Okay, basically what we're doing is we're building our way up to more and more complicated figures. We'll do triangles for quite a while, then we'll do four-sided figures, then eventually we'll work our way up to doing things that have more than four sides. Then we'll start looking at three-dimensional objects. Okay, so we work our way up to more and more complex objects. So today we're doing a little bit from section 4.1 and a little bit from section 4.2. Section 4.1 is on classifying triangles. That should all be review for you. Okay, so we're going to zip through that pretty quickly. So starting with the definition of a triangle is a polygon with three sides. In case you've forgotten, a polygon is a figure that is composed of segments that intersect at their endpoints to enclose a region. So probably in elementary school or at some point you had things like this. And if you drew it like, even with as straight as this, you probably apologize for this not being perfect. What is that, by the way? It's a hexagon. Okay, it has six sides. That's a hexagon, and although we'll talk more about this later, so is that. Okay, this is what is called, or when you saw it in elementary school where it was all perfect and everything was exactly the same, that's called a regular hexagon. This one would be very irregular. Okay, but if it only has three sides, then it's a triangle. Now we can classify triangles two different ways. One way is by their angles, and another way is by their side lengths. And again, this should be all review for you. An acute triangle is one where all three of the angles of the triangle are acute. So here's an example of what that might look like. A right triangle, notice it's one right angle. What are the other two angles in a right triangle? What kind of angles are they? They're acute. Every triangle has at least two acute angles. Okay? That's one of those things that makes a great true-false question. True or false, if a triangle has an acute angle, then it's an acute triangle. That would be false. All triangles have an acute angle. Fact is, all of them have two. It's whether or not they have all three. Okay? It sounds good, though, doesn't it? If a triangle has an acute angle, then it's an acute triangle. Nope. Now, if a triangle has an obtuse angle, it is an obtuse triangle. The other two angles will be acute. A special type, and this may be new to you. Have you ever heard of an equiangular?
Yes.
Okay. Equiangular, anytime you see the prefix EQUI, or sometimes without the I, that just means equal. And angular, I wonder what that could mean.
Triangular.
Angles.
All three angles are the same.
So equal angles. Okay? Here, this is where all the angles are congruent. And that'll always be acute because you can't have three right angles in a triangle. Or at least not in our kind of geometry. Just put it away. Joey, please put away your computer. Thank you. In spherical geometry, you can have a triangle that has three right angles. Yes. It's a good question. We'll get to equilateral in just a second. And with triangles, there's a special relationship between the two that we won't get to today, but we will on another day. Okay? But good question. All right, so that's classifying triangles by angles. We can also classify angles by sides. A scalene triangle, none of the sides are congruent to each other. Isosceles, and this definition may be a little bit different than the definition you were taught. The correct definition is an isosceles triangle has at least two congruent sides. Okay, that's an important thing that you may not have done before. Isosceles triangle has at least two sides congruent. Okay? And then an equilateral triangle, Marcy, this is what you were asking about. An equilateral triangle has three congruent sides. Now, going back to what this is saying, notice EQUI equal. Lateral. Okay? There are several words that you know that are like lateral. For those of you who know football or rugby, a lateral is where you underhanded or overhanded in rugby sideways, from side to side. You're also familiar with, because I know all of you took world geography last year, latitude, right? Which way do the latitude lines run? They run side to side. Okay, some of you were doing this, yeah. Like a ladder. Okay, so here this means equal sides. And later on in this unit, we'll talk about the fact that with triangle, those are related to one another. With other figures, you could have something that is equilateral but not equiangular and vice versa. Okay? All right, so let's classify these triangles by their side lengths. So if we're looking at triangle KYR, how many congruent sides does it have? Two. Therefore, it is isosceles. What about YRA? Do we know that any of its sides are congruent to each other?
No.
No, so we call that scalene. What about the big triangle, triangle KYA? Do we know any of its sides are congruent?
No.
No. So that's scalene again. All right, moving on. All right, here we want to classify each triangle by its angles. So if we look at triangle JAM, it gives us two of the angle measures, and we're going to talk more about this in a moment, but is it going to have a right angle or an obtuse angle? No, pretty clearly the biggest one is this 80-degree angle, so this triangle is acute. All right, let's look at triangle AME. Well, the only one they've given us here is this 20. Can we find the measure of this angle right here? Yeah, how?
180 minus 80.
Yes, why?
Because it's a straight line.
Because they're what? They are a linear pair. Remember when I promised you that linear pairs were never going to go away? They keep showing up. So if I do 180 minus 80, I get that this is 100. So what kind of a triangle is AME then? Obtuse, because it has an obtuse angle in it. And then the big triangle, triangle JAE, does it have any right angles or any obtuse angles in it? No, so it's acute.
Wait, I have a question.
Yes?
If you add the 60 and the 20 and you minus it from 180, that's 100, so that's obtuse.
I'm sorry? This whole angle is not 20. This part of it is 20. Okay? Yes, sir.
No, the big triangle is before and
Oh, well, now we haven't talked about that yet, have we? But most of you know this already, so let's go ahead and use it. Okay? He points out, what do the angles in a triangle always add up to? 180. We're going to talk about why in just a minute. I find that most students know that it's true. Almost no one knows why. It's just one of those things where you got taught it and you went, okay, and you accepted it and went on, which is okay. But so if we do this, 100 plus 20 is 120. From 180 leaves 60. And 60 plus 80 from 180 leaves 40. So how much is this whole angle at A? 60. That's 60. That's 60. So it's acute and it's also equiangular. And people frequently want to say equal angular. It's equiangular. There's only one L in it. Okay? Now, the Triangle Sum Theorem, I find that students at this age almost all know this one. Every now and then I find someone who doesn't know it, but just about everybody knows the angles in a triangle always add up to 180. For just a second, just set down your pencil and watch. I'm going to show you why. Okay? It's actually pretty interesting that you can prove that this is true all the time, not just accept that it's true. So I'm going to draw a line that goes through point S that is parallel to RT. Does everybody sort of agree that that's something that you should be able to do? And is there going to be more than one line through S that's parallel to RT? No, it's just going to be just that one, right? Okay? And for convenience sake, I'm going to label these angles 1, 2, and 3. Okay? What do angles 1, 2, and 3 add up to? 180. Everybody agrees with that. Because together they make a straight angle, right? What kind of angles are angle R and angle 1? Alternate interior. And since the lines are parallel, those are congruent. So I can substitute and replace the measure of angle 1 with the measure of angle R. And in the original, I could have called this angle angle S, right? So that's the measure of angle S. Plus, what kind of angles are T and 3? They're alternate interior also. Notice I'm going to mark them differently than the first set. So I could replace angle 3 with angle T. Because I don't know that angle 1 and angle 3 are congruent. Right? If I mark them the same, I'm saying that all those angles are the same. And I just don't know that. This is why. The angles in a triangle are always going to add up to 180 degrees. Or I can justify why, not just somebody told me one day. Okay? You can also, if you take a triangle and cut it out, and how are we doing on time? Hang on just a second. 11:15. Oh, we're doing great. Okay. I'm going to show you something. Give me just a moment. Sorry, I should have had this all queued up, but it'll only take a moment. Ah, there it is. So if I take a triangle, I can fold this up to make all those angles be at one point. So if you take the top and fold it down parallel to the bottom, take the right side or the left side, fold it perpendicular to the bottom, and then take the other side and fold it perpendicular to the bottom, look what happens. Those three angles that were up here, over here, and over here now meet up and perfectly match together to make 180 degrees. It's pretty slick. Do you want to see it again? Well, some people say, oh, you set this up. You fixed it so that it would work that way. Okay. Let's make it different. Let's make it.
What if you fix it? I think you fixed this one.
You think I fixed this one?
Yeah.
Yeah, earlier into the-
There, you didn't fix that one.
You don't think I fixed that one?
No.
Okay. Yeah.
It's an envelope. Make it as small as possible.
Set up.
Why don't you take a triangle shape and make
Yeah, you can do that. You can do it with, if you were to cut out a triangle out of a piece of paper, as long as the sides were perfectly straight, you could fold it to do exactly the same thing.
You should make kids do that, like, on the paper, like.
That's be a project.
I would have cut this one off.
So here are the angle measurements for this one. All right, shh. So angle A over here is 27.33 degrees. It's rounding it to the nearest hundredth of a degree.
So it's hard.
ABC is 127.8 degrees, and BCA is 24.87 degrees. And when you add them up, you get 180.00 degrees.
We gotta add this ourselves.
Oh, you're not going to trust me? Don't I have a trustworthy looking face?
Oh, don't start with this.
All right. So that's another way that you can show that the angles in a triangle add up to 180. So let's use that to do this problem. We want to find the indicated angle measurements. First of all, they're asking for angle RST. So from R to S to T, we're looking for this angle right here. Notice that's part of triangle RST. So all I have to do is add these two together and subtract it from 180. So 62 plus 40 is 102. I'm going to do 180 minus 102, 78. I believe. Did I do the arithmetic right?
You did right.
Okay. I sometimes don't. So I sometimes can do geometry and calculus, but I can't add or subtract. Just it's a thing.
That makes sense.
All right, now we're looking for angle SQT, which I could have just called angle Q. We have a problem though. I only know one angle in that little triangle. There are two different ways to solve the problems. I'll take a suggestion on what I should do. What's one thing you could do?
Angle R and
Angle R. I don't know which angle R is.
SRT.
SRT, uh-huh.
Yes, and SRQ make a linear pair.
Oh, okay. So one of the ways I could do this is I know that I have a linear pair here with angle SRT and angle SRQ. So I could go 180 minus 62 is 118. So this angle is 118. And then what?
Add 118 and 12 to get 130.
So 118 plus 12 is 130.
And then 180 minus 130.
Okay. So this is one way that we could do this. There is a different way that we could do it without finding the 118 degree angle. So that's all correct. I'm just going to erase this stuff. There's another way to do it. Yes.
Two interior angles make up one exterior angle, so
I'm not going to find this angle. Okay, I just said that. Yes.
The large angle add up to 180, and we have the other two angle, VST and the ST3.
Yes. What he's saying is that you can look at the whole big triangle. Don't its angles have to add up to 180?
Yes.
And if I add these two together, 78 and 12 makes 90. So now I've got 90 and 40, and I can find the other one. So 90 plus 40 is 130 from 180. We can get 50 that way also. Nicely done. Okay, interesting. What kind of a triangle is the whole big triangle then?
Right.
It's a right triangle because it has a right angle in it. And I want you to notice something. So the big triangle has a right angle, and it has two acute angles, right? 40 and 50. What's 40 plus 50?
90.
It's 90. So if I have a right triangle, the other two angles add up to 90. That is called a corollary. It's a theorem that comes directly from some other theorem. The right triangle corollary says the acute angles of a right triangle are complementary. In this diagram, and it's wrong on here, so please fix it, it's angles S and T that are complementary, not angles R and T that are complementary. I will just tell you right now, students don't use this theorem nearly as much as they ought to. You can do it the long way, but it's always faster if you have a right triangle and one of these two angles to just subtract from 90. Let me show you. Look at page 3. Okay, you could use the fact that the angles in this triangle add up to 180 to find angle A. You would have to add the 90 and the 37 and then subtract from 180. So you'd have to do two operations. Mathematicians are incredibly lazy, efficient. Yeah, that's it. We're efficient. I'm just going to take 37 from 90. Done. These two angles have to add up to 90 if this is a right triangle.
I love mathematicians.
All right, any questions about that? Okay, then your assignment is in the book.